So is this question impossible? Well, it isn't. It's just very, very difficult, although it is achievable just using the knowledge that you have from A-level physics. So this is a problem on ISAT physics. A student couldn't do it, and neither could their teacher. Their teacher, Gorilla Physics, actually emailed me. I couldn't do it, and then I put it out to some other teachers, and eventually we got the right solution. And it's beautiful when you know how to do it. So this question is about square wave charging. So you might have a sinusoidal wave that you're used to. A square wave is either kind of one, like maybe a positive voltage and then a zero voltage or a negative voltage, and it just alternates between those two fixed values. And here we have a capacitor of a certain resistance, a resistor. We've got a 12-volt power supply. So the first question, at t equals 0, the switch is closed, and we want to know the voltage across the capacitor 3.7 seconds later. So this isn't a discharging exponential decay curve, this is a capacitor charging curve. And therefore what we can say is that V is equal to V0 times 1 minus e to the minus t over RC. Now here RC is a time constant of the circuit. Sometimes it's given the symbol tau, and if we work it out from the data that we have here, we've got 35 times 10 to the minus 6 times 100 times 10 to the 3, giving a time constant equal to 3.5 seconds. So to work out the value of V, we can just put the numbers in, which gives me an answer equal to 7.83. Now, with ISAT physics, you need to be very careful about the number of significant figures. So the number that we've got is 7.8. And the units for that are going to be volts. And if we just check the answer, we're correct. Now, most people will have got that correct. That's the kind of question that you might get in an A-level physics exam paper. Now, part B gets a little bit more tricky, and this is looking at the maximum voltage. So now, rather than having a DC power input from those batteries or the cells, we now have a square wave input. We've got a time of t, and it's at a certain amplitude V0. Okay. Now, the voltage across the capacitor will eventually settle into a steady state in which it oscillates between a maximum value of plus V and a minimum value of minus V. And this is because it doesn't fully discharge or charge up over that wave cycle. And we need to find a general expression for Vmax in terms of V0, RC and T, and then find Vmax when V0 is 8, T is 2.5 and RC is given above. Now this is where I tried a few things and I couldn't get the right answer, and to be fair, I didn't really persevere. However, even though I didn't get the right answer, I was still having to think about capacitors, and it was helping me understand this subject in a little bit more detail. Eventually, I got this solution from another teacher, which I then worked through myself, so it was kind of clear in my head. And then basically, this is my working out. So it gets a little bit tricky. So you'll find that, like lots of teachers do, it's not that these things are impossible, they're just quite difficult. So the first thing we might think about is maybe just drawing a graph of what we have. So this is my graph with time on this axis here, and basically what's going to happen is that the capacitor is going to start at Vmax and it's going to discharge like this. And as it discharges, it's discharging towards the point down here, because again it's a square wave. So the point it actually discharges to down here is equal to minus V0. Okay, now that is basically going to be a big value, maybe 8 volts later on. And at this point here, the potential difference across this capacitor is going to be the difference between Vmax and this value of V0. Now it never quite gets there, because at a certain time, it's then going to start charging up again. And if we were to actually follow it, we then see that this then charges up to Vmax, and after the next cycle it kind of discharges again, and it basically oscillates between these two values. Okay, so hopefully that's making sense so far. We also know that there's this normal equation for a capacitor, which we've got up here, but for a discharge we can say that V2 is equal to V1 e to the minus t over RC. And here V1 is going to be this value up here, the initial value of that potential difference, and it's going to discharge until it gets to this value here, which I'm going to call V2. Okay, so it was at V1, and it's going to only discharge down to V2, at which point it starts charging up again. Now, here we can look at this graph, and we say that V1 is actually going to be equal to Vmax plus V0. Okay, so whatever the value of Vmax is, we add it to the value of V0 to get the total potential difference it's starting to discharge from. And the final value here for V2 is the difference between these two values, which is equal to V0 minus Vmax. And what we can now do is substitute both of these values back into that equation. So V2 is equal to V0 minus Vmax, and that's equal to V1, which is Vmax plus V0, all multiplied by e to the minus t over RC. Okay, so that's the equation, the standard capacitor discharge equation. These are the values from this graph. And drawing a graph, or kind of a plot like this as you're working out, is super important. What we can now do is a bit of kind of stuff with this. And if we maybe just multiply out the brackets and collect like terms on each side, we can say that V0 minus V0 e to the minus t over RC is equal to Vmax plus Vmax e to the minus t over RC. We can see there's some brackets we can put in, so we can say that this is equal to, well, it's equal to all of this, and therefore Vmax is going to be equal to V0 times 1 minus e to the minus t over RC divided by 1 plus e to the minus t over RC. So this is the expression which tells us the value of Vmax. Now we can then add some data into this. So Vmax is equal to 8.0 times 1 minus e. Well, the time for one complete wave cycle is 2.5 seconds. So half the wave cycle as it's discharging is going to be 1.25. And the time constant we worked out earlier is 3.5 divided by 1 plus e to the minus 1.25. And then we can just simply work this out on the calculator, giving a value equal to 1.4 volts. Okay, so let me just check that's correct. So 1.4, and the units for that are volts. Correct. Oh, I'm just going to close that. I'm just going to continue without an account. So basically, even though it starts at 8, it settles down to going between plus 1.4 and minus 1.4 volts. Okay. Hopefully that's making sense so far. That looks like an awful lot of complicated maths, but all we're doing is we're starting with an A-level thing. We're looking at this kind of graph I've got over here. We're putting the numbers in and then doing some rearranging. And there might be a quicker way of rearranging that. Okay, now the next question says about the minimum frequency. Calculate the minimum value possible for the frequency of the input if Vmax is not to exceed 1% of V0. So now what we're going to do is, if I, again, just move this over here, I'm going to do this last one in red. We're going to take this equation here where Vmax equals V0, 1 minus E, all of that. And if I just write it out again, we can also say that Vmax over V0 is now equal to 1 minus E to the minus T over RC over 1 plus E to the minus T over RC. And this relationship between Vmax and V0 is equal to 1%. So what we can say is that 0.01 is equal to 1 minus E to the value of T. Now, we don't know the frequency, we don't know the time, but the time is going to be equal to half of a wave cycle. Okay, so whatever the time is, it's going to be equal to t over 2. So this is the t, the period of that one wave cycle we're after. So that's e to the minus t over 2 divided by RC, which is 3.5. So that's equal to minus t over 7. And that's over 1 plus e to the minus t over 7. And now all we need to do is rearrange this to make t the subject. Basically, this is what we get. T is equal to minus 7 times natural log of 0.99 over 1.01. Now, if you're watching the video this far, you should be able to do the maths, okay? So I would say you can just multiply both sides by that. You can find like terms. It's all good stuff, okay? That's just basic maths. It takes a bit of time, but if you're watching the video this far, have a go at that. This is what you should end up with. And if we then just work this out, we find that T is equal to 0.14000. So that's the time period, and the frequency is going to be 1 over the time period which equals 7.14. Okay, so here that's going to be equal to 7.1 with the unit of hertz, which is correct. Now for this question here, be aware that some people, you can get the second part B incorrect and still get the final correct answer for part C, but this is the correct method. So a lot of people thought maybe Isaac Physics is broken, maybe it's been programmed wrong. No, Isaac Physics is correct. And this question is correct as well. So there we go. These are my answers, 7.83, 1.4 and 7.14 hertz. Okay, so that question there, pretty tricky. However, even if you don't quite get the right answer, the fact that you spend time having a go at these things really kind of deepens your understanding of physics. And also stuff like this is going to really help you prepare not only for your actual A-level physics exams, but other things as well. Maybe like the British Physics Olympiad, maybe for PAT tests, or if you're kind of going to university in the kind of entrance exams. This kind of way of thinking is going to really stretch your knowledge. So those were my answers. Well, actually, those were Tony Reeves' answers, kind of explained in a little bit more detail for those of you who want to have a go at this question.